What if the sun moved just 1 centimeter away from Earth? It sounds almost absurdly small, trivial in the cosmic scheme. A centimeter is barely the width of a fingernail, cutting a piece of wood, measuring a length of cloth. Applied to the cosmos, it becomes a powerful thought experiment, a lens on delicate, intricate balance that allows our world and life to exist. It prompts us to look up at the forces governing our planet. We exist on a small, fragile world, a sphere of rock, water, hurtling through silent space. Our constant companion is the sun, a star of unimaginable size and power, about 150 million kilometers away. That immense distance is hard to grasp, yet this precise separation, kept consistent over eons, defines our environment. The sun's gravity locks us into a predictable path, a stable orbit that gives us the rhythm of days, nights, the precession of the seasons, a relationship of immense scale, founded on physical laws with unwavering precision. The stability we take for granted is a perfect equilibrium. Earth is in a cosmic tug-of-war, forward momentum balanced by the sun's gravitational grip. If we move too slowly, pulled inward to a fiery demise. If we moved too quickly, we'd break free and drift into cold, dark interstellar space. Our existence hinges on this balance, a dance of motion, gravity, continuing for billions of years. Thinking about a 1 centimeter shift shows how fine-tuned the mechanism is. Not meant to inspire fear, but to evoke wonder, curiosity. A gateway to fundamental principles shaping the universe and our place in it. Exploring such small changes helps us grasp the interconnectedness of distance, gravity, energy, life itself. At the very heart of our planet's relationship with the sun is a force we feel every moment of our lives, yet often take for granted: gravity. In simple terms, gravity is a fundamental attraction between any two objects that have mass. Every object in the universe, from a single grain of sand to the most massive galaxy, pulls on every other object. The strength of this pull depends on two key factors: the mass of the objects, the distance between them. The more massive the objects are, the stronger the pull. The farther apart they are, the weaker that pull becomes. This invisible force is the master architect of the cosmos, sculpting stars, guiding planets, holding entire galaxies together. The sun is, by an extraordinary margin, the most massive object in our solar system, more than 99.8% of all mass. It exerts a colossal pull on everything, including Earth. In turn, Earth pulls on the sun, but our effect is minuscule. Earth is held captive by the sun's dominant field, an unseen tether sustaining a life-friendly orbit. Imagine throwing a ball. It travels forward, but gravity bends it downward. Earth works similarly, at grand scale. We move about 107,000 kilometers per hour. The sun's pull bends that motion into a near circle. An orbit is not just a simple circle. It is a dynamic and complex path shaped by the delicate interplay of speed, distance, gravity. The Earth's orbit is technically an ellipse, slightly stretched. Our distance changes. Perihelion about 147.1 million kilometers. Aphelion about 152.1 million kilometers. We cycle through these distances each year. Climate systems are adapted to this variation. This natural wobble is far greater than a single centimeter. The sun does more than hold us in orbit. It bathes Earth in a constant stream of energy, light and heat. This energy, known as solar radiation, traverses 150 million kilometers and powers almost all life. It warms air, land, and oceans, enabling liquid water. It fuels photosynthesis, the base of most food chains. Without it, Earth would be a frozen, lifeless rock. The amount we receive follows the inverse square law. Double the distance, and intensity drops to 1/4. This explains why our distance is critical. Too close and oceans boil, too far and the planet freezes. Move the sun 1 centimeter farther, and solar energy decreases by an unimaginably small amount. Parts per quadrillion. A single passing cloud dwarfs this effect. Daily and seasonal swings are orders of magnitude larger. In the short term, the effect is effectively zero. Our energy balance is robust to microscopic perturbations. Earth's climate is an incredibly complex system, a dynamic interplay between oceans, the atmosphere, the ice sheets, living organisms. Driven by the sun, stability depends on how energy is distributed and trapped by greenhouse gases and surface reflectivity, albedo. This machinery keeps temperature life-friendly, yet small sustained shifts can have profound effects. Earth's past shows sensitivity. Long-term orbital and tilt cycles alter sunlight patterns and align with ice ages. A constant, tiny energy deficit over millions of years could nudge trends, perhaps slightly increasing glacial susceptibility. But context matters. Volcanic aerosols, shifting currents, and especially human greenhouse gases overwhelm such a minute shift. Amid these larger drivers, a 1 centimeter solar shift is lost in the noise. The very idea that we can contemplate a 1 centimeter change across 150 million kilometers is a testament to human ingenuity. For most of history, the sun's distance was a mystery, solved through observation, mathematics, and innovation. Today, radar astronomy lets us bounce radio waves off Venus and near-Earth asteroids, time their echoes, and compute distances precisely. Combining orbital models with spacecraft data pins the astronomical unit to within meters. Very long baseline interferometry links radio telescopes worldwide to observe distant quasars, forming an Earth-sized instrument for exquisite positions and distances. This stable reference frame reveals subtle planetary drifts, essential for navigation, testing general relativity, and planetary defense. By tracking near-Earth objects with precision, we safeguard Earth. Detecting a hypothetical 1 centimeter shift showcases the observational power that enables exploration. We are no longer passive observers. We actively measure the universe. As remarkable as our current capabilities are, they keep improving. The quest for precision drives technology, promising finer views of the universe and sharper monitoring of our solar system. LISA will measure spacecraft separations over millions of kilometers with subatomic precision to detect gravitational waves, a monumental leap in distance measurement. These advances will refine planetary orbits. On the ground, giant telescopes with adaptive optics will deliver unprecedented clarity. We will tighten solar system models and search for subtle gravitational signatures, here and around other stars. Every new decimal of accuracy opens a new window, stronger tests of theory, subtler phenomena revealed. By seeing ever smaller changes, we understand orbital stability, climate sensitivity, and the delicate conditions that make our world possible. The contemplation of a 1 centimeter solar shift does more than teach physics. It connects us to a human quest for knowledge. For millennia, we've sought our place in the cosmos, from ancient astronomers to robotic explorers on Mars. Curiosity drives us to build, to theorize, and to work together across generations and borders. Science is collaborative and borderless. Global agencies, observatories, and research teams pooling data and expertise. From breathtaking images to precise navigation, a 1 centimeter question sparks lessons in scale, causality, and careful measurement. Science gives us common ground in a divided world. We share one small, fragile planet. Understanding it is our united goal. In the end, the idea of the sun moving 1 centimeter away is both a simple puzzle and a profound lesson. Immediate catastrophe is absent. Life would not end in a flash. Earth would not be flung from its course. The universe, on human timescales, is more robust than we fear. But thinking in geologic and cosmic time reveals how the smallest, most persistent changes build monumental transformations. Stability is a dynamic balance, not a static state. Science shows our astonishing ability to measure with unimaginable precision. We track planetary dances, read faint galactic light, and simulate our climate, guided by evidence and reason. Even the smallest change in the universe can mean everything for life on Earth, and so is amazing.